So how many people have heard of Semantic Scholar? Okay, thank you. And how many people use it? Okay, mechubad. And anyway, we're working on that. Those of you who don't know, it's a search engine for scientific content. Again, it's not exactly a topic that you make money on, and I'll talk a little bit more about it later on. Commonsense is the main topic. Aristo is a grand challenge where we want to use NLP and reasoning and background knowledge to solve standardized test questions. Think of it kind of like an IQ test for AI systems. Turns out to be quite tricky because in a typical science test, we don't use IQ tests, we use science tests from the state of New York. They ask questions like, what's a better conductor of electricity, a plastic spoon or a metal fork, right, or an iron fork? And you have to reason, right, that an iron is made of metal, and metal conducts electricity, and so on and so on. What's interesting is that the people who write these tests write them for kids to test their science understanding, but the science is pretty trivial, like the notion of conducting electricity. But then understanding really means to take a topic and apply it in a particular context. So you need to apply it in a common sense type of context. And that's what turns out to be quite challenging for the machine with Aristo. So just about LNNLP very quickly, it has a number of conveniences like standard ways to do training, streaming of data sets. It has a declarative syntax. So for example, if you want to define an LSTM, and who these days doesn't want to define an LSTM, you can define it in this structured way. Here are a few of the key parameters. This one is bidirectional, dropout parameter is 0.5, number of layers, et cetera, and off you go. So declarative syntax is nice, and we have a number of interactive demos on the website. I'll show you an example in a second. There's more than 20 state-of-the-art models already built in, and we have a fairly large and growing group of organizations that are using it, both universities and other types of research organizations. And I guess now I can add Hebrew University to our list of logos, and then this will shrink. Notice, by the way, the theme of happy graphs, right? We're happy. Okay, so in the context of Semantic Scholar, something that we're less happy about is what I like to call the Moore's Law of scientific publication. Maybe you notice that it's getting harder and harder to find what you're looking for. Actually, this has been going on for many years. The number of scientific publications is growing exponentially. In AI, it's literally a Moore's Law. The number of AI papers on arXiv is doubling roughly every 18 months. So no surprise there. So our hypothesis is it makes sense to use AI methods, NLP and other ones. By the way, there's still a couple of chairs. Now I get it. Some people want to be close to the food. Okay. Anyway, the problem is clear, right? And our basic premise, and you can play with it from your phone at this domain, is that we can use various methods to help guide you. So we can filter for survey papers, we can extract the key results in some cases, we can unify the papers with blog posts or even with videos, so you don't have to read the paper, you just read the blog post about it and decide whether you want to read the paper in depth, right? Things like that. So very much work in progress, but we have now more than 3 million users per month. It covers all of computer science and also all of biomedicine, everything that's in PubMed. So pretty exciting project. And we make a lot of the data, by the way, available. There's open source code and open source data if you want to use the data to do your own studies in AI, NLP, and I know it's relevant to the work some of you have done. Okay, now end of the commercial program. Now we go back to the Eurovision. No, that's already old news. Let's go back to my talk. So basically, what I'm going to do is I'm going to criticize pure deep learning, argue that there's some problems with it, and I'm going to talk about how common sense is an approach that that can help the acquisition of common sense. So deep learning, right? Is there anybody who's not familiar with deep learning? I put the question so nobody raised their hand. Even if you're not familiar with it, you're gonna, who can raise their hand and say, and what does familiar mean? But basically, here's the recipe now for writing a paper. You gather lots of training data, right? Or you grab one from European Parliament proceedings, ImageNet, Twitter, whatever you want. You apply deep learning models, right? They're lying around. Maybe you tweak them a little bit so it's original. And then you observe impressive gains on whatever task was defined, and you publish, all right? That's why, even though the MLP deadline is tomorrow, a few days ago, there were already 4,000 submissions. That's been growing exponentially, right? Which is pretty crazy, right? I think they have room for about 5 papers in the MLP. Okay, maybe not 5, but a small number of papers and 4,000 submissions. Because you have the recipe for writing a paper, what could be easier? I would actually argue that, you know, this was interesting.
Same as the writing as well.
Sorry?
Just give the data to the program.
And it will write the paper as well. Well, you know, with GPT-2, right? That is apparently that is coming. So what's the problem with this? The problem is that even though we do a really good job on the data sets involved, often we actually don't do such a great job on the actual task. Here's a couple of examples from vision. I don't know if you can see very well, but if you run a vision algorithm on this region of an image, you can see more or less a car, right? So you look at this and you say, okay, that's a car. And that's what the vision algorithm does based on machine learning. The problem is that it detects the car here, right? Because it's, you know, a convolutional neural nets, right? Sliding a window. Oh, there's a car. Never mind that it's in the water and it's smaller than a duck and or a barbour, whatever you call that thing. Anyway, it doesn't learn in context. So it's not surprising then that the performance of deep learning methods is often very brittle in the sense that you change the data a little bit and the results become very, very bad. So this is an example from a CVPR paper 2015. They keep coming up with more papers like this, right? You can make very minute changes to the image, or you can construct images that don't make any sense. And the machine learning algorithm that works so well will say this is a centipede, this is an armadillo, here this is an electric guitar, right? You can sort of see, right, something electric guitarish about this, but it's not an electric guitar. So so that's a real problem with these methods, right? If we're going to rely on them in more critical contexts. In natural language, very similar things apply. So one of the models we have in Allen NLP, and I just gave the slides here, so I don't have. I'll go through it quickly. Here's a paragraph of text. This is from the famous data set called Squad. It's about The Matrix. It says The Matrix is a 1999 science fiction film, blah, blah, blah. And then you can ask questions, and it answers them by highlighting the relevant region of the text. So this is a particular neural model. It was trained on other paragraphs. It hasn't seen this one before. You ask it who stars in The Matrix, and it says, can people in the back see? No. It says, you know, Keanu Reeves, Lawrence Fishburne, other people like that. Okay, that's good. Then I ask it, what is Neo's profession in the movie? And again, what it says here is computer programmer Neo learns this truth, blah, blah, blah. So it doesn't say it's his profession explicitly. The program figures out that a computer programmer is related to Neo and the computer programmer is a profession. And so you ask, what is Neo's profession? It says computer programmer. That's pretty good. So at this point, you might think, hey, you know, and this is one of the things that gotten people so excited about these deep learning models in AI, even NLP. You ask it, what is the machine's goal in the movie The Matrix? And it answers here, to subdue the human population. The sentence was, a simulated reality called The Matrix, created by sentient machines to subdue the human population. no mention of goals, and so on. This is quite impressive performance. At this point, I was playing with the system. I always believe if somebody tells me I have a great AI system, play with it, but you get to ask the questions. At this point, this is actually questions that I asked. I was pretty impressed. But then I asked, who is neophyting, right? And it said, computer programmer. Okay, and so this isn't so much a change in the data, but it shows you the brittleness, right? It has no common sense. It has no actual understanding of the text, right? So some of the answers are very good, and some of the answers, you wouldn't get from a 2-year-old. Then you ask it, how many actors star in the Matrix? So it realizes it needs a number, but again, it doesn't understand really that this is a year. So it says...
clothes of the agent, might be right.
Right, but it's not that smart. Anyway, you see my point. The systems that we build that do so well, right? We keep seeing the scores going up on standardized tests. Each and every one of them, if you had 15 minutes, you could break it very easily, right? They're just not very robust or resilient to errors. Another big problem is data efficiency. So for both practical reasons and theoretical reasons, it can take tens of thousands, if not millions, of examples to train and achieve this level of performance. But there are many situations where we need to work with far fewer training examples. Or even in a situation, right, where we change the distribution radically, the distribution of the test from the training, and we just have a surprise, right? If suddenly an elephant materialized here, that's not something that you've seen before at Hebrew University, I don't think. And you would have no trouble recognizing it as an elephant and reasoning about things like, I don't think the elephant is going to make it through this door, big elephant, et cetera, et cetera. So people are robust to changes in the distribution, and classical statistical machine learning algorithms are not, right? The definition of machine learning is you expect the test set distribution to be the same as the training set distribution. But that's actually a major limitation. Of course, also, common sense helps if you want to explain what's going on. But here's really an interesting point. There's a lot of interest in AI these days in safety, right? How do we build safe algorithms? Some people think about it in the context of saving humanity, right? But there are more practical contexts. I'll give you an example. For many years, I studied building software agents, right? There's the kind of things that would be on your phone or on your laptop, so you don't have to like do all the clicking and dragging and figuring out all the commands. And I imagined that you tell my software agent, who called it a softbot, reduce my disk utilization by 20%. And right, so you don't have to figure out how to do this, do compress and defrag and transfer this. It just do it for you. Why not? Well, because it comes back and it says, yes, I did that. I deleted your ERC proposal and all those silly drafts. And I also took all your data sets. They took a lot of space. I deleted those as well as the backups. And I saved you 25%. Huh? Aren't I good? So how is the softbot supposed to know? You told it reduce disk utilization. You didn't give what's called the qualification problem. You didn't tell it, but don't delete these and these and these things, right? So if a program doesn't have common sense, it's very, very hard to make it safe. There's a lot of study of this in various mathematical concepts like value alignment and things like that. I would argue that without common sense, you cannot express to a program what is harmful and what is beneficial. And if you can't express what's harmful and what's beneficial, then you can't build an AI system that's safe if you give it non-trivial powers. Does that idea make sense? So lots of very different. We'll get to that. We'll get to that. Yeah, I've been very vague. I'm going to be less vague in a minute, but it's a very fair point. It's actually a hard concept to define. But the point I'm trying to make is that why AI systems really need it for a wide variety of reasons. So, as you anticipated, let's talk about what is common sense. Wikipedia says is the ability to perceive, understand, judge things that are shared by all people and can reasonably be expected of nearly all people without need for debate. That's actually pretty much close to the best definition that I could come up with. The way I think about it is, if everybody knows it and everybody agrees about it, it's common sense. Like the sun will rise in the sky tomorrow. If it has to do with politics or Trump or Bibi, then it's not common sense because people disagree. Some things that we thought were common sense, like people should have vaccinations, turned out, at least in the United States, not to be common sense because people disagree about them. But most people agree that if I have here a book, or something, and I let go, it'll fall to the floor. Right? People don't agree that the Earth is round, so maybe that's not. So this is an approximation. John McCarthy and others, tried to formalize it in logic. This is more of a joke. The other thing that I would add is that, interestingly, computers are terrible at this, right? Despite all these successes. And the reason is that the variety of things, the facts or judgments or rules that fall under common sense is really immense. So I'm going to give more and more examples. If I put my socks in the drawer, will they be there tomorrow? I think most people would agree. Which object is flying and which is stationary in this sentence below? The sentence is, I saw the Grand Canyon flying to Los Angeles. Right? So a lot of it has to do with natural language, but also has to do with knowledge, right? If you don't know what Los Angeles is and what Grand Canyon is, you won't get this right if I replace this with X and Y, right? So there's a lot of background knowledge the computer needs to have to solve this. Here's more examples, and these are just assertions, right? Ants are small, dogs can eat rodents, water will freeze in the freezer, a match can light up a candle. Think how smart you are. Right? You know all this stuff. 8-year-old kids know all this stuff. And we don't have a computer program that even knows these basic facts, certainly not as expressed in natural language, right? Not only do you know it, but you can read it and understand it and decide this is true or false. So it's a huge open area. It's not just facts. Here's judgments. Let's say I describe to you a situation, and then I give you multiple choices. It's easy to decide, on stage, a woman takes a seat at the piano. Basically, what is she going to do next? I can give you 4 options, and you can instantly decide which one makes sense. Okay, she's going to put her finger on the keys, as opposed to other silly things. So this problem actually has a very, very long history in AI. In the 50s and 60s, John McCarthy said it's very important to study. Doug Lenat. How many people here have heard of Doug Lenat? Yeah, he's gone out of style. He used to be very famous. So in the early 80s, he very courageously decided he's going to study this problem. He built a project called Psych, and he's been studying it now for more than 30 years. And it actually hasn't been going so well. I will give a critique of his approach in a second. But he deserves a lot of credit for being the person to state this problem and then dedicate his career for studying it. And we learned actually a number of things from his efforts. Mostly we learned in the first 10 years. The last 20 years, I don't know how necessary they were, but certainly Doug, this is not fair. Doug would disagree with me. He says we're still learning a lot. But here are some of the things we learned from Doug. He started out saying, I'm going to put into the computer the knowledge that's in the encyclopedia, right? Because you need that knowledge about what's the Grand Canyon and so on. Very quickly he realized, no, we need the knowledge that's required to understand the encyclopedia. Even the encyclopedia, even a basic encyclopedia, assumes a lot of background knowledge. That's what the computer needs. So implicit knowledge is critical. It's not like we can just take knowledge that's written down or in some database and just transfer it into the computer. computer. Oh, by the way, I gave examples of factual knowledge, linguistic knowledge. There's also bodily knowledge. For example, if I go to a door and the door has a handle, it opens to the inside, I have to kind of move a little bit, right, to open the door. Otherwise, it won't work. If we're going to build successful robots, they need to have that kind of knowledge too. Right? And that knowledge that you need to move out of the way of the door, you won't find in any encyclopedia or in any textbook or in any body of text, right? There's so much implicit knowledge. Secondly, I'd like to put it, size matters. The amount of knowledge, there hasn't been a reliable estimate of the number. If I was one of those people, they love to say this in chess, it's bigger than the number of atoms in the universe. I don't know if it's bigger than the number of atoms in the universe, but it's a lot. And of course, it depends how you count, right? If I say that 3 is bigger than 2 is part of common sense knowledge, then there's a proof that it's bigger than the number of atoms in the universe. The other really important thing is you need to know how to use it, right? It's not enough to have that knowledge as a set of facts in some database. For example, Doug Lenat's Psych project accumulated a very large number of facts, a very large number of bits, but it wasn't able to use them quickly, right? And we seem to have the ability to retrieve the relevant information in, certainly less than a second. So the observation that we had at AI2 is that modern technologies, crowdsourcing, NLP, machine vision, right, all of which are based on machine learning, are a great opportunity to revisit this grand challenge, A. And B, this is the point where Google and Facebook and others don't have an advantage. They don't have repositories of common sense knowledge any more than we do, right? They have user data. But this is a great opportunity where you're in much more of a level playing field if you're a graduate student at Hebrew U compared to somebody who has all of Google's resources. The next observation, and again, this is a learning from Lenat, is that we need to have a way to measure it. We need to have ways to think about it more formally. We also just need to have a way to measure it. It cannot be scientific if you can't measure progress. So we set as our first goal to figure out how do you measure common sense. This was a key problem with Lenat's work, right? He worked on it, but there was no way to measure in this Psych project. It went on for 30 years. How much common sense does he have? Does he have, is he doing well, really well, 80%, etc.? So we said, let's make this an empirical problem. And by the way, a great analogy to Turing and intelligence, right? I don't know that we have a definition of intelligence, but Turing with the Turing test, he says, I'm not sure that I can define intelligence, but let's have an operational definition of measuring whether we've achieved it, right? And that, of course, is the Turing test. So we focus on this, and we ask, how do we create benchmarks for progress on common sense? And we said we want to be agnostic of how the problem is solved. And I'm going to skip some details here and just show you what we did. If you go to leaderboards.alanai.org, we created a bunch of tests that anybody can approach, and you can build your system externally and then take the test, and you can measure how much common sense your system has, or ConceptNet has, or maybe you think the Google search engine has it, or Psycast. Doesn't matter. It's an external test, right? You just test yourself on a benchmark and so on. And in the United States, there's something called the Machine Common Sense Initiative by DARPA. DARPA guides and a lot of the AI research in the United States by doing the ancient Navajo Indian trick of giving hundreds of millions of dollars to researchers. That often kind of causes them to move their research direction. So they have a major initiative in common sense, and what they're using, we partner with them, they're using to measure themselves is our leaderboards, which is pretty exciting. So here's an example. Actually, let me give a better one. So here's an example of the kind of reasoning we would expect to do using common sense knowledge. We describe a situation. We say, started out, Gina was hungry. And then we ended up with Gina got dehydrated. And we ask you, what are the possible explanations that she started hungry, ended up dehydrated? One is that she ate a balanced meal, and the other one is she ate a lot of salty food. right? So again, even my 8-year-old who's with me here in Jerusalem would say, because we're constantly telling him, don't get dehydrated, you're in Israel, drink. So he would say A, right? No computer can answer this type of question reliably at this point. And the point is the range of these types of things is very, very broad. And the kind of reasoning involved is not deductive reasoning. You can think of it as abductive reasoning. You can think of it as a form of natural language reasoning. The point is it's quite a difficult problem to do at high performance. And people are really good at this. Everybody in this room who speaks basic English would get like 95% on this. And if I motivated you enough, you'd get 100%, right? It's just, it's pretty trivial. Let me give you an example in the physical domain, and then I'll stop because I think, at least by example, people will understand common sense. But again, you need to break a window. Which object would you rather use? Books, a giant teddy bear, a beanbag, or a metal stool? Now, this example is interesting because what we're trying to do is trying to create a situation where you're using an object in an unanticipated way. Right, because there are a lot of systems, starting with Word2Vec and then Elmo and then BERT, that get some vague sense of objects and their associations just from billions of words, right, and just the statistical relationships between words. And those are quite good at telling you, certain things about objects. But if you want to figure out which of these 4 things that you've never used to break a window, I would guess, used to break a window, you need to have a somewhat deeper understanding of, what are the properties of a metal stool, right? Here's another example. Which object can you use instead of a rolling pin, to make dough or something? A wine bottle, a large bowl, right? We can kind of visualize it and figure it out. The computer can't. So this is an example of physical common sense. Does this make sense? So we create tests like this, both training examples and test examples, and then we ask the computer to solve this. And this is a problem the DARPA is going to be using for the next at least 3 years or so. I mean, this type of questions. They're available. They're going to be available on the web for anybody, including you, to use starting June 27th, so very soon. And I anticipate there'll be more and more papers written on this. Let me just pause at this point, see if there are any questions about what I've said so far.
So this particular test, so essentially I need to have another layer attached to any one of these concepts, not much more than that. I don't see how deep it is in the okay. Windows made out of glass, and glass is breakable in certain ways and so on. So it's not much more than one rather flat network of connection association between objects.
Right. So there's a couple of points. First of all, I think you're making a good point. Let me say a couple of things about that. First of all, we definitely don't have, when I talk about things like you need to reason and you need an immense amount of knowledge, I'm completely agnostic of whether you do this using deep learning or not, or deep learning mixed with symbolic methods, whether you need 2 layers or 3 layers or more. How do you train it, etc. I'm presenting problems. So it's entirely plausible that an appropriate neural network that's not very deep, that's trained on enough data of this sort, will do very well on this. One thing that you would need is a very large number of training examples of this sort, and those are harder to come by. So we're generating a bunch. It's not clear that you have enough there. That's one challenge. The other challenge is the one that I talked about earlier, which is we try to have this very broad range. So what if none of these items or none of these words repeat themselves in the test questions, right? I'm showing you training questions. But now in the test questions, I don't ask about breaking a window. I ask about breaking a glass in a Jewish wedding. And the example I give is, and I say, okay, you can't use your foot. What could you use to break a glass in a Jewish wedding? A beanbag, a dictionary. You see what I'm saying? So
the point I'm trying to make is this is not something which is beyond current AI and something.
Yeah.
It's within the realm of what you're trying to do anyway.
So I very much agree with you. It's also a continuum, but I would say that one of the things that we aimed for with these leaderboards, and the DARPA program did as well, is to do things where we can make progress on, right? So often these deep learning networks will do, you know, they start with 60% and then you refine them, they'll go to 70, 80, that takes time. But we wanted this to be actionable as opposed to, oh my God, we need a completely new system. So I very much agree with what you're saying. So,
is there any lesson to be learned from, I don't know, cognitive science, psychology, about how do we develop our common sense? How do people?
Yeah, so that's also a great question. Actually, the DARPA initiative, you know, not that I'm not selling the DARPA initiative, it's going, but they actually divided it in half. And half is around this, and the other half is, like you said, is actually on cognitive approaches, more like Josh Tenenbaum and his type of work. So obviously they feel there's a lot to be learned. What we know about how people learn is they can use very few examples, and they can use their bodies very effectively, right? Interaction with the environment. So my colleague Yejin Choi, for example, argues that the approach of trying to use massive bodies of text and deep learning networks is a lot more practical. It's not that it's better or that it's more accurate. It's kind of a lot more actionable. If you tell me I need to build a robot, I need to have a simulation of the child's environment, I need to build a cognitive model, it becomes a very long road. So I would say people are split on how to approach this. So a lot of people are very interested in cognitive approaches. Again, my interest is in turning this into a bona fide research problem. So it's music to my ears what you said and what you said, because people are starting to think, okay, how do I win the leaderboard, or how do I make progress on it using my methodology? The thing is that other than Doug Lenat, again, despite what I said that his approach was successful, very, 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 very few people up until recently dared to tackle this problem at all. Because how do you write a paper if you cannot measure it, or if you have to have psych to work as a proprietary database? And now we're trying to make it so it's easy to do research on it. Anybody can. That's the point of this. So what I want to do is tell you a little bit, just illustrate some of the approaches that we've taken at AI2. They're not meant to be the ultimate approach, just to show you how we've tackled some of these problems. And our Commonsense project, which is called Mosaic, is led by Yejin Choi, who's really one of the leaders in Commonsense and NLP, and was working on this problem even before she joined AI2. It's a great confluence. Don't ask me why there's a rocket here, but it meant to show we're going progress. So before, let me start, to those of you who are not familiar with psych, and quickly describe their approach and why it didn't work. So psych's approach was modern in the 80s. It was called knowledge engineering. Knowledge engineering is some of us were around back then. Is basically a lot of typing, right? Maybe you're a trained typist, but you're basically putting in the knowledge manually, which is problematic if the amount of knowledge is large. It's also it's also problematic because because it's large, very much we have to distribute the work. Okay, so maybe 10 of us or 20 of us will do the knowledge engineering. And rely on crowdsourcing, on learning either from text, from images and video, or from some sort of simulation, which would be a cognitive approach would typically be based on a simulation, are more likely to succeed and have actually been more successful on empirical benchmarks. So let me show you some of the things we do that are not completely straightforward. Let's say we take a sentence like X through Y, Oren threw the ball. You know the fact that I threw the ball, but what's interesting is we can infer actually a lot from this. And this is a paper by Yejin and her students in ACL 2017. They called it verb physics. So I can learn things like X is bigger than Y, right? Typically, not always, but typically when you throw something, like I throw a ball, I'm bigger than it. I can learn that X weighs more than Y, right? I certainly weigh more than a ball I would throw. As a result, Y will be moving faster than X. So what's interesting about this is now when I read a corpus of a billion sentences, and you can imagine for different sentences having these different types of conclusions, or at least for different verbs, I can start to learn a lot more, maybe general things than I want. So for example, if I'm interested in size, I would learn, a person is bigger than a ball, typically. Speaking of sizes, we don't just have to learn from text. Here's an interesting paper, was in AAAI 2016, about learning the size of objects from images. Because often in text, text suffers from what's called reporting bias. Often we don't tell you obvious things. If I might have a sentence that said, the cat sat in the window and looked for its owner or something, right? But you don't necessarily understand that the cat is quite a bit smaller than the window, and what is the ratio of their sizes, but you get that automatically from an image. So we can also use images and videos to learn from these things, and we can do various things like transitive reasoning, right? So maybe there's a dog in the window, but dogs are generally bigger than cats, so I can infer that a cat is smaller than the window. So basically, we have these sources of data. We can layer various kinds of inference over this data and learn massive amounts of common sense. Despite these various achievements, there isn't a system today. I used to work in a system called Know-It-All that tried to learn a huge amount of factual knowledge from the web. So I was joking, so do we have size it all, right? A system that you give it two objects and it tells you which one is typically bigger. We don't have it. Again, maybe it can build it just with 2 layers or however many layers, but the fact of the matter is that while all these things are approachable, they're actually non-trivially hard, partially because of the huge range, right? And partially because people are so good at this, right? Finally we found something that people are good at least for a while, relative to machines. It's not chess, it's not Go, but common sense. Okay, another approach I just wanted to mention is, because people are so good at this, we've done a lot of work with crowdsourcing, right? How many people have used crowdsourcing in their research? A little bit. It's very, very common in the United States in research, and it's particularly common at AI too, because crowdsourcing does cost money, and we're fortunate. I like to say that we're the combination of a university department and a startup. We're a nonprofit, we do research, we try to define ambitious goals like a startup, but we're a Paul Allen funded startup, so we're happy to have resources, for example, to do crowdsourcing and so on. So crowdsourcing has some real advantages. The biggest one is that people have a lot of common sense. It's cheap to elicit common sense from people. Here's an example of a graph that we're building, and that, by the way, everything that we're building we make open source. So again, we build this graph, you can use it, that talks about events, their causes. Let me show an example. This is from a AAAI 19 paper. Then we had about 300,000 if-then rules. I think at this point we're getting close to 1 million. And it says things like, a node in this graph is X calls Y on the phone. This is an informal phrase, right? It doesn't have precise semantics, but we connect it to other nodes. Like, for example, as a result, X might feel happy, here, X, remember X's childhood. So X might want to be nostalgic. And again, these graphs tend to be very noisy because they're about psychological attitudes and emotions and effects. But again, we have the opportunity to keep improving them. So what I'm trying to illustrate to you is how we use text and inference, vision and inference, and crowdsourcing to start and build our common sense repositories and answer the type of questions I showed you. So I'm going to show you one more case study where this gets a little bit more involved, and that's understanding procedural text. Daphne, I think you just had a paper on procedural text in a different domain. So see what you think about this. So we find that often there's text that describes some set of actions. It might be a description of a scientific process like photosynthesis. It might be a description of a cooking recipe. There's a number of different domains where this is the case. So if we take a simple scientific text, It might look like this. We have a description of photosynthesis. Here's a picture. To those of you who reason pictorially, it would have these 4 sentences. Roots absorb water from the soil, the water flows to the leaf, light and CO2 enter the leaf, and then light, water, and CO2 form sugar. Okay, this is the level of photosynthesis description in a textbook maybe for a 4th or 5th grader. The problem is that when we built deep learning methods to understand this sort of thing, understand what are the inputs, what are the side products, what are the outputs, really what happens in every stage, we saw that the neural network was actually making an enormous number of mistakes, right? So we trained it, then we fed into the learned model, we fed this kind of text, but then what we did is we created a matrix where we asked it, take the different objects, the water, the light, the CO2, the sugar, where are they at each point after each sentence, right? In other words, we asked the neural network for a very detailed understanding of what is going on. Not give me the answers in the end where it can sort of, maybe we've all had the experience of a test where we don't really know the answer, but we kind of look at it and we eliminate some of the other ones and we say it's this, right? When you're asked to fill in the state or the location of each of these objects every step of the way, you really need to understand what's going on. And we found that the program actually didn't understand very well. And the reason was that it was lacking a form of common sense. So we wrote down really some axioms that are obvious, like an entity must exist before it is moved or destroyed, right? We saw lots of examples where the neural network was first moving something and only later it was created, right? Like the sugar was moved before it was created. Or an entity cannot be created if it already exists, right? If we already have water, typically in these situations, right? Obviously there's counterexamples to each general rule, but in 4th grade textbooks, you don't create the entity in the text if it already exists, et cetera, et cetera. It turned out that it was actually relatively simple to then provide knowledge of these axioms to the neural network. I'm not going to go through all the details, but effectively what we did is we changed the loss function to, including into the usual encoder score, we gave it a common sense score. So whenever it made the prediction, it paid a penalty if the prediction wasn't sufficiently commonsensical, right? If the prediction violated either soft or hard the constraints. And then we trained this up on a training set that was built using the common sense model. And we found that, that we were able to achieve somewhat better performance. Again, all these models don't capture the axioms perfectly, but we started with a rule-based system. The F1 score was 35. Then we started building increasingly sophisticated networks, and these are R2 where we put in the common sense constraints, both some hard ones and some soft ones, and we got pretty substantial gain, F1 score for 35 up to 53. Still a lot of room for progress. And then again, this data set, which is called ProPara, and our code is also available on the internet. So to your point, it gives you a little bit of the feeling of the kind of work we do. We are gradually trying to encode common sense and trying to find general methods of doing it, right? This common sense was pretty specific. We used hand-encoded axioms, which is very nice because they're easy to state, but problematic if you want to do it in a very scalable way. Okay, I want to leave a little bit of time for questions, so I'm going to end here. Common sense facts and methods are only very partially understood today, and extending this understanding is the key problem facing artificial intelligence. That's something, sounds like something I would say. I didn't say it. Who do you think said this?
Turing.
Great guess. Anybody else?
Robert Wayne.
Okay, you're getting me. It's a very fundamental. But and if he didn't say it, he should have said it. So actually, it's McCarthy in '83. He also said something very similar in '56, right? So from the inception of the field, and I'm sure Bar Hillel and Turing and others would agree, from the inception of the field, this has been a key problem. It's been relatively understudied. And again, why? I like to use this metaphor that common sense is the dark matter of AI. What I mean by that is, what is dark matter? It actually is very pervasive, we've learned, in the universe. And physics has struggled to study it, right? Because it's there, it affects gravity and various other forces, but we have a hard time perceiving it using standard instruments. So what we're trying to do with these leaderboards and other methods is build the instruments that make it relatively easier to study common sense for you and everybody else. Thank you. Leo, you've been very patient. Please.
Thank you. First of all, thank you for a great lecture. I'm going to play a little bit the devil's advocate because I've been in this field. I was in this field a long time ago. My take on your lecture is a very pessimistic view because the questions you put were the same we had 30 years ago. And you very nicely surveyed the effort of doing the knowledge engineering and all these things. And the same problems that you had with rule-based systems, you now have with deep learning. You have much more data, you can build that. But basically, and please correct me if I'm wrong, I didn't get it that there was any progress in this field in the last 30 years. And so, please tell me what was the progress in the last 30 years.
Right. So I agree with you that this is very challenging. So again, we can make progress on it. It's very challenging. And I also agree with you about the progress in a certain sense. But let me tell you why I'm less pessimistic, because we're trying new methods, right? So the methods that were available to us last time we worked on this are very, very different than the ones we have today. The ones we have today do benefit from more computation and a different class of algorithms. Crowdsourcing is a new thing. So I don't think we're going to solve it like this. There's a lot of nuances here. Yeah, so I do think we'll make progress. A huge difference, right, other than the methods, is the fact that we can evaluate the progress. So if you go back to the previous methods, you had an intuitive sense that these problems were hard, didn't solve them, but there wasn't actually measurement. Now, in AI, whatever we're working on, we do expect there to be an empirical measurement relative to a data set, and that's what we're putting forward. So we will be able to...
It's very partial, because you're the one creating the tests. So for the narrow fields, it's much easier to create. Here, even the evaluation is problematic. I mean, you nicely showed these tests, which we couldn't do and we still cannot do, but it's still very biased, the way you create the evaluation. So it's still difficult to do the measurement. And in that sense, I would even not advise a graduate student to even get close to this problem, because most likely you're not going to be able to do any problem.
So we'll have to agree to disagree, but I just point out that actually the tests are partial, that's true, but that's exactly why we can make progress. So any empirical benchmark has its limitations, but it has been a good way for the field to make progress. Other questions, and also Hebrew too, yeah?
Yeah, continuing what he said, what makes you think that your the letterboard thing gets the scale of the common knowledge and the common sense knowledge? Because I agree that all the questions there involve common sense, but even if someone got 100, there could be a lot of other common sense knowledge that you just haven't thought of. What makes you think that you've encompassed it, that a high score means it really does have good reasoning?
Yeah, it's a great question, and I would say a couple of things. First of all, I agree with you that I was trying to say getting 100, let's say, on this, I don't want to use overly formal terminology, but it's necessary, not sufficient. So actually, we don't have programs, as I emphasized a few times, that can even get 80% on these tests. But you're right that if we got 100, we built a program to get 100 on all of these, that wouldn't mean that the problem is solved. It means that we've made progress. So this is a gradual approach, and it's a very reasonable one. But to your point about the scope, when we're dealing with language, actually the number of verbs and nouns, of common sense nouns, is circumscribed. For example, by lexicons like WordNet and so on. So we can do things, and we do, for example, separate the nouns and the verbs in the training and in the test, and then select them randomly in the test in various ways. So we cannot argue that we've covered all of common sense, because again, I still didn't give a formal definition, but we can argue that we're not just, in some little corner shining a flashlight if we're covering all the nouns and verbs in English.
I'm not sure, going back to the definition of common sense, what's not clear to me is whether you really need to define it as something separate, or it's just a derivative of understanding text. So suppose that you do solve the problem of text understanding. Now go over all the internet and extract all you can from this text. Won't you have common sense?
So it turns out that systems like Elmo and BERT, right, which are effectively doing a form of what you're saying, have a surprising amount of common sense, because these connections, like the ones you talk about, I just need another layer, do filter their way through these very large corpora. So I would say that you're right, that this notion of common sense is close to the kinds of analysis that we do of text and vision and other things. It's still the case that when we do a good job, the systems that just work on the sentences seem to be, much better than random, but limited. So it looks like they require some common sense, and people are really good at it. I still think that your point stands. Like, is this, geometry is distinct from algebra. Physics is distinct from chemistry, although, on the edges they kind of combine, right? Physical chemistry and, algebraic geometry, But basically we agreed those are separate fields. Should there be a subfield of AI called, common sense, or is it really like a type of domain inside NLP and a type of domain inside vision? I don't think I've made the case that this is completely different. In that sense, I agree with you. I hope that I made the case, and this is different from the other folks like Leo who are questioning me, that this is ready to study, that you can make progress on it, and that's really my point.
Another question. What's the role of common sense in poetry, in poetic text?
I'm not any more qualified to answer that than you, but that's probably not the first place that I would go. Aesthetics is again a whole other question of how do we build aesthetics into AI programs, but it shows you that there are domains of thought that are very different. And the one thing I would highlight is that this isn't a reaction to the work on Go and chess and so on, right? There's a feeling, certainly among the general public, right? People who don't build AI systems, AI is solved. Look, we have a Go system, right? So in artificial...
Watson and debaters and things like this,
that's right.
Definitely using common sense in a very successful way.
Well, that is arguable, but you're absolutely right that we also have systems in...
So there's actually huge progress in the last 30 years that you really compare things fairly, just to answer Leo.
Yeah, I would argue, for example, if Watson, unfortunately that system doesn't actually exist today, but if Watson tried to take our tests, I think it would do very badly. The IBM debater, again, it's built for a different task, but I would conjecture that it would do very badly on these things. So again, we don't cover all of common sense, but this type of common sense they don't have. Yes?
In order to see whether the kind of test boards that you're working with are really a metric, how about scaling down? Supposing you take all the sentences you could form with the vocabulary and the cat in the hat and test for contradictions and things that violate common sense.
Yeah, I think that...
Ask whether, have you created a closed set, or is even that open?
I think your suggestion is a great one. And we have just created a few of these. There's a few on the website and a few more that we created for DARPA. We definitely don't have the monopoly or even the best approach. I think that using closed vocabulary would be very interesting. The only thing is that, again, because we want people to get engaged, we try to create large training sets. So for example, with the cat in the hat, an interesting question becomes, what's the training set? Now, if you say, look, the training set, you find the training set, whatever you want, or the training set is the writings of Dr. Seuss, that's fine, but a lot of people don't like to approach things unless there's already a training set available.
You could take the book. 60-word vocabulary, I think, something like that.
Yeah, and people's favorite methods won't do very well with 60-word vocabulary. But I'm not. This is very much open, right? So I love that idea too. Other.
So unfortunately, we're out of time.
Okay.
Let's thank Oren again.
And thank you.